All right. Hello, Physics 135 students, and welcome back for our week 7 virtual class lecture number 8. First of all, apologies, this is a bit later than I was planning on, and as you will probably notice from my voice at some point today, although maybe not, I've been sick for most of this past week. I'm going on my conference trip starting on Sunday, so I'm really hoping that I get better soon, but we'll just see. Okay, so first we have a new icebreaker. If you had to be allergic to cats and dogs, or alternatively, if you had to have seasonal allergies, and for that, usually that's just pollen, but let's make this a little bit more aggressive and say pollen plus grass plus hay, which my sister and dad both have. Uh, which would you choose and why? And for myself, I really love dogs. My sister and dad are actually also allergic to cats. Um, but I really love dogs, so I would not want to be allergic to cats and dogs. I would probably choose to have seasonal allergies, although I'm lucky enough to not have any. So for yourself, please go over to Discord. Ideas that you can get to know each other a bit better, although it does seem like maybe that was a lost cause this semester. Always worth a try, though. Maybe in the future I'll actually kind of make it part of the grade. But anyway, it would be great, nevertheless, if you post on the Discord. But please email me your answers that we continue to build some rapport as the semester goes on. We're nearing the halfway point. And speaking of that, a couple important upcoming deadlines. First of all, your second deadline for the semester-long research project, which is the annotated bibliography, that is due this coming Sunday, March 1st. And also important, exam 2, which is not posted as the recording of this video, but I will hopefully be posting your week 8 lecture very soon. I plan on posting it before I leave for my trip on Sunday. So the good news is we'll be a little bit more ahead of schedule finally. Um, and then I plan on creating that corresponding quiz. And then this exam 2 is going to be covering the first 8 weeks. So both this set of slides as well as the next set of slides. And it's going to be due at the end of week 8, which I think is maybe unfortunately at the beginning of your spring break, but you will have at least a week to work on exam 2, which means that you can complete it before you leave on your spring break, or maybe not leave, maybe still study. Okay, and then for today, we're going to cover some of the real key ingredients that are required for understanding the origins of the universe and nucleosynthesis. Namely, we're going to talk about light and its properties, some basics in terms of spectroscopy, and relatedly Kirchoff's laws. For spectroscopy, there are also Kirchoff's laws for circuitry, which is a little confusing. And then we'll be talking about the Doppler effect. I guess to some extent, all three of these are intimately linked. But I think that this is roughly the order we're going in. And then regarding these were kind of a carryover from last week, which we didn't get to. I've decided, unfortunately, not to include this material. Maybe I'll include some of it next week. But all this would be a new like course prep for me set of materials. I would like to. The Great Debate is a really fun topic. I really like history myself, and so I would like to get into these different components. And a lot of you asked questions about about like Williamina Fleming and some of the other Harvard computers. So I would like to include this material, but I just don't know realistically. I didn't want to delay this any further, so I decided to not include that material today at the very least. Okay, so first we have 4 goals for learning, which are your first 4 attention checks. Although, admittedly, you will encounter some attention checks before you answer all of these 4. So we'll be talking about what is light. We'll be talking about how we experience light. We'll be discussing how light and matter interact, and there are a couple of different ways that that takes place. And then last but very importantly, we'll be talking about the electromagnetic spectrum. And I guess I shouldn't really be saying last because we'll actually kind of start and then end with the electromagnetic spectrum. So regarding like how we experience light and what is light, let's just put it this way. In terms of the way that we perceive the world around us, we can hear from anywhere from like 20 hertz to 20,000 hertz. Remember, this is cycles per second, or in other words, this is a frequency. So this is a really big range. It's only a couple, I guess, orders of magnitude logarithmically. But so we have a pretty impressive capability hearing wise. Although in terms of the so-called frequency of an Earth day, that is way, way below our auditory range. And then we can observe a set of wavelengths between 400 and 700 nanometers, which is, it'd be a really kind of like gross number to think about in terms of the frequency. So that's why we switched to wavelengths here. And so this is a pretty narrow, if you think about it, it's about a factor of two in wavelengths compared to this, factor of three orders of magnitude in terms of auditory range. And just as there can be a huge, huge range of sounds, there is also a huge, huge range of the spectrum that could possibly be seen. So the range that could possibly be seen, we could say goes from 10 to the minus 4 nanometers all the way up to 100 or even 1,000 meters. There's not technically limits on the long side, and gravitational waves could be much, much longer, although they're not part of this electromagnetic spectrum, of course. And similarly, there's not necessarily a limit on the small side, although we think that there are kind of limits to the highest, just in the sense of the highest energy object and how far it can propagate from its source. So that would be related to highest energy cosmic rays ever produced. And there is a limit as far as how far they can propagate from their sources, which kind of places a limit on the smallest wavelength that is at least possible for us to observe. Maybe at some point we'll get to being so powerful of a civilization that we can make our own supermassive black holes and insane cosmic ray accelerators. But for now, we're nowhere close to that. All right, and so then in terms of this visible spectrum, again, that's a very, very tiny range, 400 nanometers to about 700 nanometers in between the UV and the infrared. So in terms of how we experience light, one way that we know part of the nature of light is due to the warmth of sunlight. And this is telling us that light has some energy associated with it. And this also indicates that light is actually a wave or has at least wave-like properties, which we'll explain in a moment. Now, in terms of this flow of energy that we can measure from sunlight or other sources of light, we typically do this in terms of watts, in terms of SI units for this class. Although, admittedly, astronomy research does not really use the System International of Units or the International System of Units, SI. So in real astronomy, we typically say erg per second with a admittedly more antiquated unit system. It would be better, maybe, if astronomy research switched to SI units. Okay, so in terms of why we know that light is a wave based on the fact that we receive that energy, this kind of includes two parts, one of which we learned a while ago. So we talked about waves previously. This is a slightly different definition where we can say that a wave is a pattern of motion that can carry energy but doesn't carry any matter along with it. So remember that we talked about how light can exist in a vacuum, whereas sound cannot exist in a vacuum. Um, and so the fact that light is able to move through a vacuum does mean that it can move without carrying matter with it. And so in this analogy, if you throw a rock into a pond, you see a set of ripples. Those ripples might move a leaf up and down, but they typically don't move the leaf. Now that's a little bit of an oversimplification, admittedly. If you drop like a boulder into this pond, then you can create a water wave, which admittedly it's not just the perturbation in the water itself, but it's due to the gravitational force that you end up with that wave kind of curling over, and then it can actually, move material. But for a prototypical wave, it is, again, carries energy but not matter with it. All right, and so here's another example of a frog in a pond. All right, and then we've talked before, again, about how waves can be longitudinal, like sound is, or in other words, compressive, like a slinky. And then we can also have waves that are transverse, in other words, that are up and down, like this jump rope. And apologies if you heard that noise, I have to blow my nose, so there might be, unfortunately, some kind of disruptions today. Moving on, in terms of light, so we talked about how light can be a wave. Light can also be a particle, though. And even though light can be expressed as a particle, nevertheless, the so-called particle of light called a photon can be associated with a wavelength and frequency, which is maybe kind of confusing if you think of particles as not being really wave-like. But this is kind of a core part of quantum mechanics that anything that is a particle, including or can be considered a particle, like an electron or a proton, actually does also have a corresponding wavelength and frequency. And then for a photon's energy, this actually is a little bit more simpler than things like an electron, where the energy depends on the velocity of that electron, because an electron can have kinetic energy. Instead of photon, its energy only depends on its frequency. Or you could still express this as it depending only on its wavelength. And now a little bit of a philosophical digression regarding, or digression regarding, this dual property of light or dual property of kind of like the universe in terms of waves and particles. So you might have heard this before in high school, or you might hear about this later, that light is both a particle and a wave, which seems like a contradiction if those are kind of either ors of a particle having like a definite shape versus a wave having really more of an indefinite shape. I would prefer to say that light and all the matter, everything in the universe, has wave-like properties and particle-like properties, suggesting that neither model alone is sufficient. And for myself, I tend to think of everything as being ultimately more wave-like, and just when the frequency becomes so freaking high, that wave becomes indistinguishable from a quote unquote particle, especially if the wave packet is quite small. So a little bit different than string theory, but kind of in that same vein. On the other hand, there is, and I place very high regards actually on and David Bohm, who was a physicist that was kind of prolific in the 1950s or so. The de Broglie, and excuse me, I have a little typo, unfortunately, in de Broglie's name. The de Broglie-Bohm pilot wave theory is kind of on the other side of the aisle. Actually, de Broglie's first pilot wave theory was kind of along my side of things, where de Broglie thought of there being a U wave, or in other words, like a particle wave, in addition to the quote unquote pilot wave that tells the particle where to go. Nevertheless, kind of subsequent descriptions of this, the idea is that you have like this wave in addition to a particle. So there's actually both. Uh, but the more real thing is the particle, and the wave is just kind of guiding the particle along, which there are certain attractions to this. Now, de Broglie and Bohm, this is a theory of hidden variables, or is a hidden variable interpretation of quantum mechanics. And this was really lambasted by some of the key, you know, uh, key proponents of the quantum revolution. So people like, um, not really Schrodinger, admittedly. Um, so some of the key people behind the quantum revolution, like Heisenberg, would be one good example, uh, as well as Max Born, really kind of lambasted this theory. And von Neumann, who is a very important physicist, came out with a book in early 1930s that seemed to disprove any sort of hidden variable theory as being in contradiction with the experiments that support quantum mechanics. Now, David Bohm in the 1950s kind of rediscovered de Broglie's pilot wave theory because he was very upset with the Copenhagen interpretation that was really largely pitched by Max Born, as well as some other folks. And David Bohm pointed out that actually von Neumann's um, proof was kind of invalid, and actually John Bell a little bit later was even more of a strong opponent against the Copenhagen interpretation. And John Bell came up with a set of inequalities that were meant to be able to prove or disprove whether there could be local hidden variables. Whereas, admittedly, David Bohm was interested in a non-local theory, which John Bell did not like because that still breaks the more typical concept of of causality as being local causality. So now there have been a number of experiments. The Nobel Prize in I think 2022 was awarded to Elaine Aspect and some of the other experimentalists that showed that there cannot be causally local hidden variables. And again, so for David Bohm himself, he that wouldn't bother him too much. He uh, preferred the idea that quantum physics really showed that the universe exhibits non-local causality. David Bohm was very into Buddhism and this concept of oneness that really are more, maybe not atomic, but are more deconstructionist or kind of part by part theories of the like more modern theories of the world are kind of inadequate. And kind of interestingly, this idea of oneness of the universe, if you think back, this is the same sort of thing that Zeno was advocating for in his paradoxes, since again Zeno belonged to this school of thought of Parmenides, who again thought that the universe was all one. So this is a digression, admittedly, but I think that understanding the world around us, or at least trying to think about the ramifications of physical theories, is very, very important. And therefore, for your next attention check, which is really the first one by and large that you're addressing, I'd like you to spend 30 to 90 minutes investigating either the de Broglie-Bohm interpretation, which I finally spelled correct, and you might want to consider pilot wave theory on Wikipedia, although there are a variety of sources you could consider. Or you can think about your own interpretation regarding the dual nature of light and, again, really all matter in the universe. Now, usually I'd like to suggest that you do these attention checks one by one, but because I don't want you to spend 90 minutes and then like another 2 hours on this class, that would be too much. I'm actually going to suggest that you hold off on attention check number 5 until you otherwise finish this lecture. Again, the idea is that each lecture should be about 2.5 hours of effort. Some of you will go faster, and so that's fine. So for some of you, it won't be 2.5 hours of effort, but I want on average this to be about 2.5 hours of effort, and particularly no, everyone goes at their own pace, but I don't want any student spending more than 3 hours per lecture. So there's going to be some dispersion. Anyway, so again, don't necessarily pause right now. Determine how long it takes you to go through the rest of this recording and addressing each of the attention checks, and then go and spend kind of whatever remainder time you have for attention check number 5. Okay, so moving on, in terms of still thinking about the like what is light and about how we experience light and really the fundamental properties of light. So we have learned before that there's this relationship between the speed of a wave, the wavelength, and the frequency. And you all learned about how old Romer uh, found that the speed of light was very, very fast, although it was not actually calculated to be any certain speed until a little bit later with, I think it was Cassini. Then in terms of the energy of a wave, again, energy just depends on the photon's frequency. Or you could, of course, rearrange and express this in terms of the speed of light and the wavelength. Now, in terms of what this h is, this is some proportionality constant to get us from units of frequency to units of energy. And the value is extremely tiny. In other words, the energy of any individual photon is very, very small, which is, of course, a good thing since the light emits a ton of photons every single second. All right, so in terms of how light and matter interact, there are really three, or we could say four different ways that light and matter interact. The first is through scattering, which we could break down into reflection and refraction, although admittedly we've already talked about refraction a little bit, and you all will learn more about this will or have learned more about this in second semester interphysics. Then there is the process of emission of light and absorption. We'll admittedly go a little bit more into the atomic nature of emission and absorption, probably next lecture, but a little bit in the future. And then fourth, although this is really to some extent a non-interaction, is transmission. So for transparent objects, well, there's just kind of no interaction, admittedly. So maybe this is more like three and a half ways that light and matter interact. Nevertheless, there are some objects that are not perfectly transparent. There are some objects that we can describe them as being opaque, which means that they block or, in other words, absorb light. So again, really, kind of still absorption here. But nevertheless, transmission is important, as we'll discuss. All right, excuse me. Now, regarding reflection and scattering, uh, in terms of how we experience this, if you've watched a movie, or for that matter, if you're simply, looking at your computer screen, the way that we primarily see the world around us is through reflections. Now, a computer screen, admittedly, is a little bit cheating. It does have light emitting diodes where there is some actual like emission technically, but for an actual movie screen, usually there is a projector, and therefore you're seeing the scattered light. And if you don't consider like your laptop screen, essentially everything around you in the room, you will be seeing due to actual reflection. And actually, I typically try to turn my screen brightness kind of lowish, where I still get some, I think, of the light through reflection. A lot of it is just the LEDs, of course. All right, and then in addition to reflection, you can have also, combinations of these different effects. So in terms of scattering, one of the easiest ways to think about this is passing light through a prism where there's really going to be some transmission through that prism, but then there's also scattering. The shorter wavelengths scatter more, the longer wavelengths scatter less, which is why we end up with a rainbow when light gets passed through a prism. So the red light ends up scattering less, which is why it is closer to the origin point, whereas the blue light scatters more, or violet light scatters more, which is why it ends up farther from the starting point. And so this happens not just for pieces of glass that we make, but water droplets cause rainbows really for this same reason. All right. And now for this next part, I am going to paint a scene for you. The idea is that there's a cold winter day with some snow on the ground, and you have the sun shining, and you're inside, and you have a mirror and a lamp. So I'd like you to try to sketch the scene, first of all, and then try to list as many interactions of light and matter that we've talked about so far, at the least, as you possibly can before we proceed. So just a reminder, those could involve reflection, could involve refraction, could involve transmission and scattering. So go ahead and pause this video and work on attention check 6. Okay, unpause. So hopefully you came up with some sort of picture in mind. This is the picture from not your textbook, but the textbook that I have used for some other courses. So if you all have taken Stars and Galaxies with me, it's admittedly some pretty familiar material. So there are many different instances of interactions between light and matter that you could give. Reason why snow is so bright is because it scatters in essentially every direction. Actually, it scatters a little bit more forwards than backwards. Um, and anyway, so we have scattering off of snow. If there's any sort of object outside, like a tree, whether it's a nice green redwood tree or some deciduous tree that has, most of its leaves gone, nevertheless, you would see that tree due to the reflection. And really, that reflection is of the color that you see. So if you see a deciduous tree that has no leaves, it's brown, it's because the white light from the sun is partially getting absorbed by that tree, but the brown light is getting reflected. Whereas for, again, most trees that have leaves, they mostly have green leaves because they absorb, well, the other colors and they reflect the green light. And then similarly in your room, maybe there's a chair, presumably there's some sort of lamp that's on, maybe not, maybe you don't have any lights on aside from your computer screen, which would still be a light source, as well as like a window, which lets some light in that maybe has bounced off of the ground, etc. Maybe you have a mirror in your room, maybe not. I personally do not. So there are lots of different interactions. And keep in mind that, again, there is refraction in our eye, which causes the light to get focused. And then ultimately, there's absorption in the rods and cones, which allow us to see the world around us in grayscale as well as in color. Okay, so next we have our attention check number 7, as it turns out. So question, why is a rose red? All right, so rose is red. Well, it could be emitting red light, like our computer screens are emitting primarily the colors that we see. But no, really, most of the things that we see that, do not have LEDs or do not have some sort of light associated with them itself, a rose is really not emitting red light, it is reflecting red light, as we talked about for the trees example a moment ago. All right, so again, the rose is reflecting red light. Now, we've talked about really the four most important kind of properties or ways that light interacts with matter. There is another interaction, so to speak, which is, or really a property of light, which has to do with the fact that light can be polarized. And this is actually kind of important in terms of understanding inflation and some of the stuff that we admittedly don't spend very much time talking about at all, but maybe uh, I think most of you have not chosen to work on inflation for your project, which is fine. But uh, one of the more interesting parts that we will cover at the end of this class is related to understanding the origins of the universe and particularly why the universe is so flat and isotropic. And there are certain predictions, unique predictions from inflation regarding the polarization of the CMB. So regarding polarization just itself, so light can really have like any sort of vibrational pattern, but if we pass it through a filter, then we might block out part of the ways that light can vibrate and only end up with some pattern which is up and down or left and right. There's also so-called left-hand circularly polarized and right-hand circularly polarized. So admittedly, it's a little bit more complicated than this picture is showing, but the idea, I think, it does get it across pretty well. So if you pass two filters that are at 90-degree angles, then you perfectly remove all light, which usually we do not want. Usually we just want to remove some of the light, especially if we're using polarized sunglasses to avoid glare, etc. And the way that this typically works is that the light that's reflecting off the highway tends to be vibrating with a very particular pattern. And so sunglasses are designed, at least typically, to be orthogonal to that roadway glare, so that we can still see while we're driving and not be quite as affected by the roadway glare. All right, and now for the electromagnetic spectrum, really kind of attention check 4 of the first 4 that we were discussing. So we've seen before, like, okay, we have gamma rays all the way through radio. To give a little bit more detail in terms of scales that are considered for radio, this is like an entire football field down to the scale of, say, a baseball or a golf ball. And then as we get to infrared wavelengths, we're already astonishingly small scales. Infrared is already at the scale of like a cell, and visible light is about the size of a single bacterium. So in other words, a very small cell. Uh, and then at even smaller wavelengths, like in the ultraviolet, we're about the size of proteins. So, very small components of cells. And then when we get more to the X-rays and gamma rays, we're really more of on the scale of atoms or even nuclei for the gamma rays. And there are different ways to express this as well in terms of sources. We'll talk a little bit about the different types of sources moving forward here with some examples. Now, in terms of how this light actually gets through the atmosphere, we actually miss most of the light from the universe. It's really only in the optical and as well as in a certain band in the radio that the light makes it all the way down to the Earth. In a variety of different wavelengths, we can, for example, for Sophia, which I think is getting decommissioned, go up, to the stratosphere and measure the infrared. But essentially, every other wavelength, from gamma ray to X-ray, etc., we need space-based telescopes to directly measure. Now, for gamma rays, you can see it goes a bit farther than X-rays or UV, or some high UV anyway. For gamma rays, there are so-called particle showers where you can indirectly measure them, but it's still very, very challenging to get any sort of localized direction. For directionality, it's really much more ideal to have a space-based telescope. All right. So we just talked about this. One thing I kind of glossed over is that, okay, there's a window for radio wavelengths. The longest radio waves, though, we also don't have access to, and that's because of electrons scattering around in the so-called ionosphere. Those totally block out like the 10, or in other words, decimeter wavelength photons. And for that, we need to again go to space, but those are so freaking huge, it doesn't really make sense to send up a Earth orbiting satellite. Instead, what has been proposed by different scientists is building a so-called lunar crater radio telescope. This was first proposed, I think, only about 10 years ago. It's a bit fanciful, although it would be really freaking cool if this got made. The world's largest telescope on the Earth is FAST, the 500-meter aperture spherical telescope in China. The idea is that, well, we're kind of running, for one thing, even for like radio dishes on the Earth, we can't really go that much larger than that. Whereas, whereas on the moon, there are nice big craters. So if we just choose some nice, like 1 kilometer diameter crater, then voila, we already have like, we don't have to carve out like something. We can just set up a wire mesh and receive the light that is, kind of coarsely grained or coarsely received. For really long wavelengths, we don't need something like a whole big telescope dish. We just need the mesh to be smaller than the wavelengths that we're trying to capture. So if we care about 10-meter size signals, then our mesh can be, of order like 1 meter gaps, or maybe 0.1 meter gaps, which are still pretty big. All right, so this would be really, really cool. The idea is to actually build this on the far side of the moon so that we don't have to deal with all of our AM and FM radio or all of our other radio noise that we produce on the Earth. And then we'd be able to detect this band of light that we have no idea what we might expect, because no one has ever measured these wavelengths before. So I think really fascinating. In terms of how we observe the world around us, so this is the crowd pulsar, and you can see in particular that there's some compact object very clearly in the X-ray, whereas in the optical, you really just see the surrounding nebula. And then admittedly, you get a very different point of view in the radio and infrared. So really going as multi-wavelength as we can really helps to clarify the nature of objects, and you learn more about this sort of thing in Stars and Galaxies. For this course, we're going to really focus more of on the properties of the not circumgalactic medium, but the cosmic microwave background eventually, and large scale structure, maybe a tiny bit. Okay, so in terms of uh, like sources of light or how light interacts with matter, let's think about visible light first. So for your attention check number 8, in this image where we're seeing like this hand, so is this visible light emitted by the hand? Is it absorbed by the hand, transmitted, scattered, or reflected? Go ahead and pause the video and think about that. Okay, unpause. So again, we we don't have any like sort of like screen on this hand. There's no real bright feature as the sunlight that is causing us to see this hand in this particular image. So this is all scattered slash reflected light. Now for X-ray, all right, so we have a different image also of a hand. In this case, we are seeing bones, and then we're kind of not seeing the space in between the bones. So for X-ray, for the skin and muscle of a hand, does X-ray light get emitted from the skin and muscle of a hand? Is it absorbed by the skin and muscle of a hand, transmitted through, or scattered or reflected by? Now, in terms of understanding this, one thing I should mention is this is a negative image. So we see the bones, but keep in mind this is a negative image. All right, so now go ahead and pause and try attention check 9. Okay, so unpause. So the fact that we do not really see the stuff in between the bones in this image really means that the X-ray light is not interrupted by the skin and muscle. So in other words, X-ray light is transmitted through the skin and muscle. It's rather unimpeded by and large. Whereas for this next attention check, think about for the bones in the hand. Go ahead and pause the video. Okay, unpause. In this case, the X-ray light is really absorbed by the bones in the hand. So that's why we see the bones in the negative. Remember, it's really the bones are the shadows, but we're taking the negative of the image and then we see the bones really clearly. All right, so we have another hand now seen in infrared light. You can see that there is some hot spots and some cold spots. Now, just in general, though, for that infrared light seen in the image, is that emitted from, absorbed from, transmitted from, or scattered, reflected from the hand? All right, so admittedly, you wouldn't necessarily have a lot of idea here. Maybe you're tempted to say, oh, it's always scattered, reflected. But notice that what we're seeing here, there's just darkness aside from the hand. So it's not really reflected light from the sun anymore. We are actually glowing in the infrared, as this will become a little bit more clear a little bit later. But everything emits at a certain characteristic wavelength. In the infrared, that is the wavelength that our bodies emit at. So answer here is A. All right, and then one example of UV light the sun emits in UV light. Okay, so gave away this attention check 12, but A, the UV light seen is actually emitted by the sun or emitted from the sun. All right, and then attention check 13, a little bit of a different question, but related to what we've covered. So the higher the photon energy, is it A, the longer its wavelength, B, the shorter its wavelength, or C, energy is independent of wavelength? So go ahead and pause the video and try that while I blow my nose. Okay, and the answer was, in this case, that the higher the photon energy, the shorter its wavelength. So maybe you were tempted to say that, oh, photon energy is only related to the frequency. But I did say that you can switch out the frequency and the wavelength based on the speed of light or the speed of a wave formulation. So photon energy is proportional to frequency, but inversely proportional to wavelength. So answer here is B. All right, so in summary, what have we learned? We talked a lot about the properties of light. We mentioned that photons are particles of light, but also that light can be described in a wave-like fashion with of course, a wavelength then, as well as a frequency. And that as far as this light wave, actually, I didn't mention this, but I could have mentioned that related to polarization, this is vibration of electric and magnetic fields. So that in terms of the vibration and removing some of the vibrations, it is due to having certain materials that block out these vibrations of electric magnetic fields along a certain axis that we can filter out or polarize light. Okay, and then in terms of how we experience light, the idea is that just due to sunlight or due to the warmth of sunlight, we know that light is a form of energy. We can also see that by like with lasers being used to move objects around, etc. And ultimately, light it comes in many different colors that can end up being white light, or it can be you can take white light and then disperse them or refract these different colors into the whole rainbow. All right, in terms of how light and matter interacts, we talked about how matter can emit light, absorb light, transmit light, as well as scatter light in terms of like reflections and refractions. And really, the way that we see the world around us is intimately related to these interactions between light and matter. Regarding the electromagnetic spectrum, one thing that's important to keep in mind is that just by our eyes alone, we cannot see the vast range of the electromagnetic spectrum. But all of those wavelengths from gamma rays through radio, even though we cannot see them, we still say that they are light because they're these photons that have a characteristic wavelength. And we call this the electromagnetic spectrum because of this property of light vibration between electric and magnetic fields. Okay, so moving on, we have another set of 4 attention checks or goals of learning. So first, we're going to talk about the 3 basic types of spectra. These are Kirchhoff's laws. Next, we're going to talk about how light tells us what things are made of. And we're going to, in particular, talk about how we learn about the temperature of distant objects through light, as well as how we can figure out the speed of distant objects. So these are, again, this is more of a fundamentals day. Although I feel a little bit bad we didn't get into the history. On the plus side, the book is really good about that. So hopefully you all have been enjoying the book. Okay, so moving right along and into attention check 14. In fact, we're going to talk about these 3 basic types of spectra, all 3 of which actually are evident here as will become clear as we move along. Um, so the first type of spectrum is a continuous spectrum. And a continuous spectrum comes from a hot and opaque source, or you could say a hot and dense source. And that can be a solid, it could be a liquid, it could be a hot yet dense gas. There are a lot of different phases of matter that can produce a continuous spectrum. And we know it's a continuous spectrum if we take a prism and we see a full rainbow. In other words, we see that there is a variety of wavelengths that we receive with no obvious gaps or peaks in it. Whereas for an emission line spectrum, this is Kirchhoff's second law, that a tenuous gas will emit light at very particular wavelengths that depend solely on the composition of that gas, as well as what I would say is its ionization or excitation state. But to make this a little bit simpler, you can say it just depends on the state of its ions, atoms, or molecules. And so the result of ten the result of this tenuous gas is an emission line spectrum. In other words, we see certain peaks at very characteristic wavelengths that are related to, again, the composition of the gas. If the gas has a large variety of materials, you'll see more lines potentially, and it depends on the, you could say maybe just the temperature, but it's not really just the temperature alone. It depends on the ionization state. In addition to temperature, uh, being related to the ionization state through collisional excitation and de-excitation or collisional ionization, you can also just have a really strong non-thermal source like cosmic rays or UV photons or X-ray photons, etc., that can also pump the states of a gas, kind of like for a laser, for example, or a monochromatic laser, I should say. All right, third type of spectrum we have is an absorption line spectrum. It's really the subtraction of the last two. So if we take a continuous light source and then we have a tenuous cloud of gas that is intervening along the line of sight, then we still get, most of that continuous spectrum. But instead of emitting now, instead, that gas will absorb some of the light that passes through it. And so we end up with these troughs or deficits in the amount of light that we receive at very particular wavelengths, which is again indicating what the composition of this intervening cloud of gas is. And admittedly, in astrophysics, it's often very much easier to notice something in absorption compared to an emission. Because usually for these tenuous clouds of gas, it's not like the sun where they're really beaming. There's really a very small amount of light that they produce in emission, despite potentially being thousands or tens of thousands of solar masses. All right, moving on. Now, in terms of how light tells us what things are made of, this is actually the solar spectrum, which, again, Williamina Fleming and a lot of the Harvard computers detail, and maybe I will include a little bit more about them next time, not this time though. So the basic idea is that every single transition that electron can have in an atom depends, one, on the change in energy, whether it's going from the so-called orbital fifth state down to the orbital third state, etc. Uh, and it depends on the type of atom. So because there is such a particular set of wavelengths that occurs, we get chemical fingerprints, so to speak, from the absorption and emission line spectra. And therefore, by measuring where there are, either excesses for emission line spectra or deficits for absorption line spectra, we can figure out what particular wavelengths are present. And then we can figure out actually not just the type of atom that's responsible, but we can also figure out the properties of that atom in the sense of it, what's its excitation. And then if we kind of assume that's in collisional ionization equilibrium, then we also learn about the temperature of the object as well. But usually for emission and absorption line spectra, you don't know for sure that's in collisional ionization equilibrium. So you really only get the composition, and then you need more information to learn more about it. Sometimes you don't. Again, it's not about the temperature. Sometimes you more of learn about the ionizing environment. Like there's a lot of O and B type stars that are producing a lot of UV radiation. Again, more about that in stars and galaxies, though. So, for one example, this is a hydrogen atom that has a very characteristic line at 656.3 nanometers. This is the so-called hydrogen alpha line that the universe is very, very bright in because there's so much hydrogen. And the Balmer line is one of the like lower energy configurations that happens very, very frequently. And then there's some other transitions that do occur but are not quite as bright that are at the bluer parts of the spectrum. All right, and again, we can notice the presence of hydrogen not just in emission, but especially at larger distances, we more primarily notice the presence of hydrogen in absorption from, say, background quasars at times that are, more than half the age of the universe from now. So more on that kind of later, much later. Now, in terms of fingerprints, it's not just hydrogen, of course, but every single atom has its own fingerprint and molecules for that matter, although the molecules get really complicated. All right, so again, we can figure out the state, and it's not just about helium versus oxygen, but we also learn, again, whether it's oxygen plus or neon plus 2, etc. So we learn about the ionization state in addition to the composition. All right, so I mentioned that from emission and absorption lines, we don't necessarily get the temperature. We learn the composition and the ionization state. But we can nevertheless figure out the temperatures of most distant objects with admittedly an assumption, but a quite good assumption, it seems like. And this has to do with really how objects tend to glow as they get hotter and hotter, as in this case of taking a iron rod, like an iron poker, and sticking it in a fire. For essentially all large and dense objects, think about the continuous uh, emitting or continuous spectrum objects. For essentially all large and dense objects, not necessarily hot objects though, essentially all large and dense objects emit thermal radiation. So this includes that incandescent light bulb that we were considering for Kirchoff's laws, does also consider humans, the Earth, other planets, stars, etc. It's just that for us and planets, etc., we don't obviously glow in the visible. We're a lot cooler, and therefore we more primarily emit in the infrared. So clearly, this thermal radiation spectrum depends on something, it depends on its temperature. And actually, the amazing thing and the wonderful thing about a thermal radiation spectrum is that really the only thing it depends on, it doesn't matter the composition, it doesn't matter whether we're considering you or me or a planet or a star. These objects emit just based on their temperature for the thermal part of the spectrum. So for thermal radiation, there are really two key components here. First is that hotter objects emit more light at all wavelengths or all frequencies per unit area. And then the second key part here is that hotter objects will emit photons with a higher average energy. So you can see for this blue 15,000 Kelvin star, it emits light at all wavelengths, emits more light at all wavelengths, and its kind of peak wavelength here, which is related to that higher average energy. Its peak wavelength is bluer compared to the peak wavelength for our sun, which is a yellow or greenish star, or for a 3000 Kelvin star, which is much more red, or for us humans, where we emit primarily in the infrared. All right. So in terms of this difference, it is a there is a power of 4 difference in the amount of light that gets emitted. So there's a big change here. The sun being 20 times hotter than a room, average room temperature is around 300 Kelvin or around 20 Celsius. The sun's surface is about 6,000 Kelvin. So this being about 20 times different compared to room temperature, which would be maybe way over here, the sun ends up emitting 20 times, uh, not just 20 times as much light, but 20 times to the power of 4. So in other words, 160,000 times as much light. So a lot more. Whereas for a light bulb, that maybe would be around 3,000 Kelvin or so, it emits only about 15% of its light in the visible spectrum and most of it in the red part. So this is considered a big waste. On the other hand, I don't know, I really hate fluorescent lights. And part of it is that the nice thing about light bulbs with tungsten, although there are a lot of negatives in terms of the energy efficiency, etc., is that the blue part of the wavelength is actually suppressed. So there is a so-called Rayleigh-Jeans tail here, where if you go from the peak to redder wavelengths, this drops as a factor of wavelength to the -2. Whereas if you consider bluer wavelengths, there's an literally exponential suppression. So therefore, it's kind of nice that for tungsten, we really get almost no blue light, so we can go to sleep more easily. You can have LEDs that are focused in the red. It's a little bit harder to get those worked out. And I don't know, it's possible that there's some nice properties of receiving as humans some infrared light, even though we don't need it to see. Okay, so enough on that kind of external diatribe. Moving on, so colors and temperature. So there are different ways to express this. Some people say that red light is cold. I prefer to say that red light is a little bit hot. And for visible light, this would be a little bit hotter. And then for blue light, that would be hottest. Although actually astrophysically, the white light is really these objects that peak in the UV, and then they're so freaking bright because this Rayleigh-Jeans tail that all the other colors just blend together and we end up with white light. So it'd really be more of red light, a little bit hot, blue light, hot, white light, which is more UV peak, hottest. Um, so it kind of depends on what you're considering exactly. For a candle, I've marked this as white light. Maybe in the future I'll change this to being red light hot, kind of more orange or yellowish light hot, hotter, and then blue light hottest. But the key takeaway here is that just generally as you go to higher temperature, you get more energy. And in other words, that means that the particles are moving around faster. And particular for solids, like most of the world around us, the faster that these electrons move, the faster they end up vibrating, and therefore the smaller the wavelength of the emitted light becomes. All right, and then again for astronomy, it's a little bit different where, technically we have red, blue, white, but actually for the white light stars, maybe I'm misidentifying this a little bit. Um, so definitely the red stars are the coolest. For stars that are kind of yellow or green, like our sun, those are hotter. For blue stars, those would be considered the hottest. I think actually though that as far as our human eye is considered, the white stars are typically the ones that peak in the UV. Although if you have filters, then you can identify which ones are really the bluest, and the UV stars would have more blue light because that first part of the thermal radiation properties, it'd have more blue light compared to a star that just peaks in the blue from its temperature. All right. So thankfully I've made this disambiguous. I don't have like a white or yellow or green star in here. So which attention check 18, which one is hottest? A blue star, a red star, or a planet that emits in the infrared? Well, kind of easy, but this one is a blue star. Planets are way, way cooler. But also if this was a star that only emits in the infrared light, like a black dwarf, then still the answer would be A. All right, so attention check number 19. Now, why don't we glow in the dark? So I'm gonna not answer this one for you. Go ahead and pause the video and try to do it yourself. Okay, unpause. Still not going to answer this one. If you're wondering about this, do feel free to email me as part of your, I think this is part of your quiz. It might show up in your test as well. And next we have attention check 20. These sorts of diagrams probably will play a role in your test. So do give these diagrams a serious try. And I believe I only have one for this particular diagram, but go ahead and try to address attention check 20. Okay, and for this one, I will mention that for the different types of spectra, if we just had a continuous light spectra, A would be the answer. If we just had an emission line spectra, actually C or B could potentially be the answer, or rather, just C would be the answer. For this absorption line spectra, it has to be B, because there is a star here, which is a continuous source, and then there is an intervening cloud, which causes that absorption. So again, absorption line spectra, only possible for B. All right, now for the Doppler effect. So we've talked about how we can learn about the temperature of objects. Now let's talk about how we learn about the speed of objects. So this has to do with the fact that the wavelength of an object depends on the motion of uh, uh, maybe let me put this a different way. The wavelength depends on the motion of an object. So if a train is stationary and we hear its whistle, then a person ahead and behind will hear the exact same wavelength. If a train is moving towards one person and it whistles again, then really keep in mind that the noise that we hear from the whistle is a set of waves. And the waves will have a set of so we can imagine that they're expanding spherically, and so each wave is closer together for the person where the train is approaching and farther apart for the person that is behind. And hopefully this person does not get run over by this train. So this is exactly the same thing in terms of what we hear as well as what we see. Again, light is also a wave. So for a light source that is moving away from a person, we see it redshifted, whereas if a light source is moving towards a person, we see that light as being blue shifted. And so in other words, for a continuous light spectrum, we really cannot tell because we just see, that full spectrum. We would maybe be able to notice that the peak spectrum has shifted slightly to the red or slightly to the blue. But by and large, we only can notice this for emission or absorption light spectra, and primarily for absorption light spectra. All right, so again, for emission line spectra, it's possible, it's really admittedly a little bit challenging to notice these Doppler shifts, but it is possible in emission. So in this top case, let's say that this is what we measure at a laboratory. If then we measure these, notice that there's the exact same, distance between these lines, exact same number of nanometers. And keep in mind that we measure these lines not just to, 1 nanometer, but really to very high precision typically. So we can notice these patterns very effectively, and machine learning is very good at this now. Then we can identify whether an object is moving away from us, if it's redshifted, if it's moving kind of faster away from us, further redshifted. We can tell if the object is moving towards us or even faster towards us, depending on how blue shifted that light is. So really in terms of, we get some knowledge of towards and away, but we also get the speed in terms of just how much, like quantitatively, the light is redshifted or blue shifted. So in terms of, again, the Doppler effect, we only get part of the motion. If we know that an object is moving exactly transverse to us, which we can figure out from proper motion for very, very nearby stars, then we don't get any sort of Doppler effect. Again, we have to use different techniques to get the velocity. For the most distant objects, we have no idea what their transverse speeds are. So keep in mind that the velocities that we measure are really a lower limit on the speed. And it's only in cases where a star is perfectly moving away from us or perfectly towards us that we would get its full speed. And that can happen, especially if we think that objects are moving randomly in the sky, then we can build up a statistical sample and figure out the distribution of speeds. And even though we lose out on the transverse speed, we can figure out pretty well what the speed should be just from the distribution, and assuming that the orientations of the speed are random. Okay, so let's say that we measure a line in the wavelength at 500-ish nanometers. We measure the same line in a star, has a wavelength of 502-ish nanometers. What do we learn about the star? Go ahead and pause the video and try this attention check question. Okay, so unpause. So in this case, the line is redder. In other words, it's longer wavelength. Red has a longer wavelength than blue. That means that this star is moving away from me. So A. All right, and then here for attention check 22, good. Which star is redshifted? The colors here are not a friend. Ignore the colors of these stars. Which star is going to be redshifted based on its motion? Okay, so again, this is kind of important for your quizzes and probably for your test. I'm not going to answer this one for you. So please do email me if you have questions. And then in this case, same diagram, just changing the question. Which star will not produce a Doppler shift? This one I'll answer B will not produce a Doppler shift because it is not moving towards or away from this eyeball here. But B is moving orthogonal to the line of sight of this eyeball, or we could say observer. All right, and then another really important sort of diagram as far as your quiz and probably your test goes. For these objects with spectra shown, object A, B, C, D, which object is moving away with the fastest speed? All right, so moving away with the fastest speed, in this case, the answer should be A, since it has the wavelength shifted farthest to the right. Now, maybe you're asking, well, how do we know that it's moving away? maybe object A is the lab frame at rest, and B, C, and D are all moving towards us at some speed. Well, moving away at the fastest speed, you can think of moving towards us being negative, so 0 would still be moving away with the fastest speed, I would claim. Um, so I would still say object A, but maybe a little loophole there. Certainly they're not moving at the same speed, and none of these other make sense. So again, by process of elimination, you can get to object A. All right, so in summary, we have learned about the three basic types of spectra: continuous spectra, emission line spectra, and absorption line spectra. We have further discussed how light tells us what things are made of in terms of uh, each atom having its own fingerprints, and really each atomic state, I should say, having its own fingerprint. And now we can figure out what atom something is made of, or molecules actually, by looking at those so-called chemical fingerprints in the spectra. Now, in terms of how light tells us about the temperatures of external objects, not just planets and stars, keep in mind. Again, basically all large and dense objects emit a continuous spectrum. And that continuous spectrum, if it's thermal radiation, it only depends on the temperature. And in addition, for the spectrum of thermal radiation, we can therefore backtrack. If we measure the spectrum, we can figure out the temperature of an object. We don't actually have to measure the full spectrum. If we just find out where that spectrum peaks, that is also good enough, actually. And then last, in terms of figuring out the speed of distant objects, we use the Doppler effect to tell us just how fast an object is moving towards or away from us, and we can figure out quantitatively the speed, at least as a lower limit, but also when we have enough objects and we can do some statistical analysis, we can figure out the speed more precisely. And that particularly works well for like globular clusters where there are around 1 million stars that are in a pretty dense ball where they probably are moving kind of randomly. It's a bit harder at the very, very highest redshift universe, though, where we just have low number statistics. Okay, so that's all for today. Hope that you all enjoyed the lecture. A little bit of a shorter lecture, I guess, is how it turned out, although hopefully you did take, decent pauses for addressing the many, many attention checks. And don't forget to go back to attention check 5. I really have had fun historically thinking about the nature of light, and I hope that you all enjoy digging into this yourself. All right, take care and bye bye.